Welcome to Applied Bioinformatics. In today's lecture, we're going to look into the generation of multiple sequence alignments. A beautiful example you can see right here. You can find it when you travel to Prague, and you see how the different versions of Prague in different languages beautifully align, and you see a conserved pattern P-A-R-A, and then the different endings depending on the language. In our setting, it will be looking a little bit more like this. You see some sequences and you see a cysteine, a tryptophan that are highly conserved, and this must clearly have a very good reason because all of the other positions were variable. So very likely the cysteine and tryptophan in these sequences play a very specific functional or structural role. Now, one idea is that it's actually not really so difficult to do a multiple sequence alignment. We know how to do it in 2D with a two-dimensional dynamic programming matrix. We could just expand this matrix into 3D. So here we have three sequences, QGL, DMNVQ, and DQLF. And instead of a matrix, we've got a cube. And what we're looking for now is the shortest path from the bottom right back cell to the top left front. Before that, we have filled the cells, of course, in a similar manner as we have done with a two-dimensional matrix. So considering the example over here and the path that is drawn in it, we get the following alignment. See, for example, in the top left front that the two Ds are consumed while the path is not going down, so the Q stays unaffected. And that corresponds in the alignment to the two aligned Ds in the first position and a gap in the last one. Now, how can a sequence alignment be extended from 2D to 3D or to any number of sequences? We have to consider different alternatives how the associations are being made. When there are two sequences, then there are three possibilities. We have a replace, an insert, or a delete. When there are three sequences, there are 7 cases. We have a replace, or in fact also a match, but for all three positions, we consume a character, or we have 3 cases where 2 characters are consumed and 1 isn't. We have 3 cases where 2 characters are gaps and 1 character is consumed. This can be more generalized, and for m sequences, there are 2 to the power of m minus 1 cases. Why is it 2? Well, because in every position, we can either have a gap or we consume a character. Now, why do we have the minus 1? Because the configuration that we have 3 gaps is not acceptable. So therefore, that possibility is removed from all of the possibilities. Now, how do we deal with that situation? Essentially, we can make use of our existing dynamic programming algorithm, but how do we rank in an alignment if there are, for example, 3 characters? Let's say 2 alanine and a valine. How should that be judged? Or we see 2 gaps and alanine being consumed. There's a very simple answer to that, and it's called the sum of pairs. The sum of pairs is exactly what it's saying. We're summing up all the pairwise scores. So if we have, for example, 3 characters, then we compare all pairs of them, the first to the second, the first to the third, and the second to the third. And we simply add up all of these individual values. Now, how to do the pairwise comparison, we know. We have done that before. We use, for example, substitution matrices, or we have our simplified scoring scheme that just distinguishes matches or mismatches. But generally, for 2, we know how to do it. So now here's a little bit of notation. So let M be the multiple sequence alignment consisting of the sequences S1, S2, Sm. Let S prime J be the sequence Si with gaps, so it means the projection, so this is what we took out of the multiple sequence alignment. And let S, in brackets, S prime I, comma, S prime J, closing brackets, be the score for aligning the sequences I and J. And then the final score is the sum of all pairs I and J. So the sum of pairs for the multiple sequence alignment M is equal to the sum from I equal to 1 to M minus 1 over the sum of J equal from I plus 1 to M, and then we take the individual score S of S prime I and S prime J. Why is the sum over J starting at I plus 1 and not at 1? Well, the answer is that otherwise we'd be repeating the comparison between Si prime and Sj prime and that Sj prime and Si prime. Let's consider a concrete example. S1 is equal to AVP, S2 AVT, and S3 PSVPT. We get the corresponding alignment, as you can see it on the right. And now the question is, what is the score? Let's assume that the match counts as 1, mismatch, insertion, deletion as -1, and if we have 2 gaps to be considered, we treat that as a 0. Now let's see what we're getting out. So we have to compare the first to the second, the first to the third, and the second to the third. So let's compare the first to the second. So in the first to the second, we have 2 matches, A and V. We have 2 gaps, they don't matter. And we have a deletion and insertion. So overall, that means +2, -2, equating to 0. Let's also look at 1 to 3. So there we have 2 matches, V and P, and the first position is a mismatch, the second position is a deletion, and the third is also deletion. So taking all of that together, we get a -1. Something similar happens for sequence 2 against 3, so overall we get a score of -2. Now let's consider this as we're trying to go beyond 3 sequences. Let's consider m sequences of length n. This means that the matrix we're considering has n to the power of m cells. Now, we argued already that for each cell we have to consider 2 to the power of m minus 1 cases, and this gives us a total of 2 to the power of n minus 1 times n to the power of m. Now let's make this number a little bit more tractable by putting in practical numbers. The median human protein length is n equal 375. And let's now assume we're considering 30 sequences, which is not really too much. We have previously already examples of 50 sequences to compare. So for 30 sequences, this would give us 2 to the power of 30 minus 1 times 375 to the power of 30, and that is roughly 10 to the power of 86, and that compares to the number of atoms in the universe at 10 to the power of 80. It's clearly prohibitive. We must look for an alternative, which can be progressive alignment. And at this stage, we know already, as always, there is no such thing as a free lunch. If there comes up an algorithm which is not prohibitive, when the basic approach that we want to take is prohibitive, that's already clear at this stage. There must be some kind of payment. But let's first see what the algorithm is. The idea of progressive alignment is to first of all do pairwise alignment and to generate a phylogenetic tree. So this we have done over the past 2 lectures, so we know how to do it. And we can actually apply all of the methods we know. We can apply hierarchical clustering, but also neighbor joining. And so we can root the tree with a neighbor joining. And in the very end, this gives us an order in which we can sequentially align the sequences, because we want to start with the 2 sequences that are the most similar to each other. And then bit by bit, we expand our multiple sequence alignment and we add 1 sequence at a time to an existing alignment. Now, as we're adding a sequence, we have to modify our algorithm. We know with a basic 2-dimensional algorithm how to align 2 sequences. And essentially this boiled down to looking at the values north, the values west in the matrix, and the value northwest. And northwest meant we're consuming a character in both of the sequences. North and west meant we're consuming 1 character, and in the other sequence we're leaving a gap. Now, how does this change if we're adding a sequence to an existing alignment? And here it's again the sum of pairs that comes in. We make it very simple. The position in the sequence, that means possibly the gap or the character that we're consuming, is compared to a position in an alignment, which can consist of multiple residues or multiple gaps or mixtures thereof. And we simply break this down into sum by comparing the individual sequence and the column of the alignment position by position individually. Before we dig further into detail how the algorithm works, let's just do a quick estimation of what that means for computation. So M sequences of length n square was the dynamic programming matrix that we need, and for each cell we have a maximum of m square comparisons for the sum of pairs. So in total we have m times m square times n square. So that's overall m to the power of 3 times n to the power of 2. Now let's assume again the median human protein length of n equals 375, m 30 sequences, so we get a total of 30 to the power of 3 times 375 to the power of 2, and that is roughly 10 to the power of 6, in contrast to 10 to the power of 86 for an n-dimensional cube. And 10 to the power of 6 is a computation that is fully doable and no problem at all. So let's look at how the algorithm is going. So we have sequences as 1, as 2, as up to Sm as input. We have a variable c that contains the current set of alignments, and we start our algorithm with making c the empty set. And now we add to c all of the sequences as individual alignments. So this is kind of a little trick in that we say a sequence in itself is already the most simple alignment there is. So for I equals 0 to m, we expand c and add to it the alignment that contains Si. So now we're iterating once again through this. So from 0 to m minus 1, we pick two alignments, AP and AQ from C. At this stage, we're just randomly picking them as they come along, and we remove both of these alignments from the existing set C, and we create the alignment of AP and AQ. We call it AR, and this AR is added to C. By the very end of this iteration, C contains one single final alignment. Why is that so? Because in every step we picked two alignments from C, we removed both of them, and we added one new one. Yeah? So in every iteration, the set C is reduced by 1 in size. Now let's go back to the question, how can two sequences be aligned? How can two alignments be aligned to each other? Well, the answer is very simple. We run the normal pairwise dynamic programming with a sum of pairs as scoring. So every position is now not an individual residue anymore, but it's rather a column of residues from the alignment at hand. And how do we compare one column of one alignment to another column of another alignment? Well, we simply add up all of the pairs of possibilities. So the first position in the first alignment gets compared to the first position in the second alignment, the first in the first against the second in the second, first in the first against the third in the second, and so on. And we do that for all possibilities, and we simply add up all of these individual scores. The individual scores we know how to rank, because either we have a scoring scheme for match-mismatch, or we have something like the substitution matrices, but these individual ones are single characters or single gaps, and we know how to deal with them from the previous lectures. An important problem remains. In the algorithm as I've sketched it to you so far, we simply pick the alignments as they come along. But that is not very good, because we can make poor choices in the very beginning, and they lead immediately to a deterioration of the overall alignment, when instead we would have done a good choice in the beginning, the overall result would have been better. And here comes a trick. We guide the generation of the progressive alignment by an existing phylogenetic tree. But let's first let me give you an example. Why is a guide tree needed? We want to align Peter, Per, and Petro, and alternatively, we change the order and we align Peter, Petro, and Per. Now let's consider first that Peter and Per get aligned. And for the sake of this example, which I try to make as simple as possible, let us assume that we get out the alignment that you see there in the top left. So Peter is aligned to P, gap, gap, ER. So the E of Per is aligning to the second E of Peter and not to the first one. It's a little bit artificial, but that was the simplest example I could come up with. Now, let's assume we got that alignment, and now the third sequence we get is Petro. So we align Petro, and as we have agreed already that the E's that should be aligned is the second E of Peter and the first E of Per, this forces us that the E of Petro is also aligned to the second E of Peter. But this is clearly, as we can see by looking at it, a poor choice, because the T in Petro would nicely align to the T of Peter. And the R of Petro again is fitting nicely. So by having made the choice of aligned E's in Peter to Per, we influence and we reduce the possibility for choice of aligning the E of Petro. So overall, in the alignment, as you see it in the bottom left, we have 7 gaps. And this is worse than the 5 gaps we would get if we first align Peter to Petro. Because if we do that, the algorithm will force us to align the E of Petro to the first E of Peter, because otherwise the T's wouldn't match. Now, once we have committed to associating the first E's, and then we add pair, then we also automatically enforce that the E of pair is aligned to the first E of Peter and not to the second. Overall, we have a better alignment with only 5 gaps. So this is a simplified example to illustrate that the order in which we're making choices about the alignments is playing a role for this algorithm. Does the linkage method change order of processed sequences? So if you think back, we discussed already that the linkage method can have an influence on the tree that is being generated. And we had a simplified example in one of the previous lectures in which we were able to generate 2 different topologies of trees without changing the original data, but just changing the linkage method that we used in the clustering. So let's consider this example. We have A at a distance of 1 to B, so A and B have the lowest value and they get clearly linked to each other. And now the question is, what does single linkage determine A and B to be like in comparison to C and D? And single linkage is taking the minimum. So for C, that's the minimum out of 2 and 4, so that is 2. And for D, that will be the minimum out of 3 and 5, and that is 3. Now on the other hand, complete linkage is taking the maximum. So the maximum of A and B to C, the maximum out of 2 and 4 is 4. And the maximum out of 3 and 3 for AB's comparison to D remains 3, as is the minimum. So this is the overall result that we have. In the single linkage case, the next closest are to A and B is C, whereas in the complete linkage case, the closest to A and B is D. And that means, yes, it can be the case that the choice of linkage method is influencing the order in which we're choosing the sequences for the alignment in the multiple sequence alignment with progressive alignment. So just be aware that, as with all of the other analyses, the choices that we make for algorithm and the choices that we make for the data highly influence the outcome that we're getting. Now this brings us back to Clostal W. So this is again the screenshot from the paper from the mid-90s of Clostal W, a really kind of the most widely used tool for multiple sequence alignment generation, cited over 50 times. So just to repeat again, the first step was the generation of a distance matrix holding all pairwise comparisons of all sequences. The next step is the generation of an unrooted tree by neighbor joining. And the next step was the routing of that tree to generate a guide tree. And then this guide tree is being used to select the order of sequences which are used for progressive alignment. There are other tools. A competitor to cluster W is muscle. It's also very highly cited, over 13,000 times. And muscle follows a more refined strategy, as is depicted here. So the underlying sequences are organized in a k-mer distance matrix. Then hierarchical clustering is applied using the UPGMA method. Progressive alignment is being applied, and then another distance measure is generated from that multiple sequence alignment. Another clustering step is applied, giving tree 2, and again progressive alignment is being applied. Then the sequences are partly deleted, subtrees are generated, realigned, another multiple sequence alignment is generated, and the scores are compared, and possibly these last steps are being repeated. To cut a long story short, the details do not matter here for our purposes, but muscle is following a more refined analysis structure that cluster W is doing. And now we may wonder which alignment is the best. We discussed this already for the 2D case, where we said, so if the choice of scoring scheme is ours, how can we decide which scoring scheme is the best one? And we argued we need a ground truth, and we discussed this and said, for example, that the ground truth can be structural data or it can be functional data, and we can simply pick the substitution matrix and the scoring scheme that is recovering the most cases from this ground truth. Something similar can be done for multiple sequence alignment. And that was, in the early 2000s, the Ballybase project, which aimed at generating a reference dataset which was based on structural alignments. So here you see such a picture. So carefully, sequences for which structure was accessible were aligned structurally. And the correspondences that emerged structurally were taken as ground truth and compared to the multiple sequence alignments as generated by cluster W and muscle. But of course, as is the case with any type of evaluation, the creation of this ground truth can also be questioned. So for example, the screenshot of this paper from Nucleic Acid Research in 2004, there the author of Muscle was investigating in detail the quality of the Ballybase alignments in comparison to the muscle alignments. And he picked out one specific example that you can see depicted here, where the muscle alignment that was automatically generated had clearly a better score and created a better alignment than what was in the Ballybase reference dataset. So that means that at the very end of the day, it's difficult to decide on a ground truth that cannot be questioned. But be that as it may, cluster W and muscle remain two very widely used tools for multiple sequence alignment generation, and generally, if one sets aside such details, they do generate good results. And of course, all of these methods are ultimately only there to generate hypotheses. They're there not to set a one and for all truth into stone, but rather to generate ideas of which residues could maybe carry particular function and be of particular importance. And therefore, it is not really of such strong concern whether one tool is a little bit better than the other one. The ultimate verification is always a wet lab experiment that is validating the hypothesis which maybe these tools have helped to generate.